Welcome to the Java Programming Language course from eduonix. In today's lesson we will learn about the architecture of the Java virtual machine. Let's start by referring to our core Java syllabus. In today's lesson we are in topic 1, the Java Programming Language, and we'll be looking at subtopic A, the architecture of the Java virtual machine, and the JVM in capitals refers to the Java virtual machine. Let's learn something about the architecture of the Java virtual machine, or JVM for short. The Java virtual machine is like a virtual computer, and it's what we call a stack-based machine, and the nature of the stack is what we call in computer science LIFO, which stands for last in, first out. So with a stack, you can think of this as being like a data container where we can put data in and we can get data out. And a LIFO stack means the last thing we put in is the first thing we can get out. So that's a little bit about its architecture. Now here I have a schematic of an old computer from the 1970s. And new computers are all basically on the same chip. But back in the 70s, you had different chips for different functions, and things were laid out. There were connections between the chips that you could see physically if you opened up the computer and had a look. And in modern computers, you don't see that. So we can use this schematic and this understanding of a real simple computer to gain some insight or understanding of the architecture of the Java virtual machine. By the way, if you're finding this schematic a little bit hard to see, just find this document, Java language document, in the documentation. Now, this is a schematic, as we said before, of a simple computer. And we have a central processing unit, a data bus, a control bus, some registers, and a cache. These are the essential parts. And what we're going to do is look at the analogous or the analogy in the real Java virtual machine. So I've laid them out to try and show how the different parts of the Java virtual machine relate to the different parts of a simple computer. So basically, the registers for a simple computer are the memory. Data is stored in registers, and then the data is moved backwards and forwards between the central processing unit and the registers on the data bus. This just moves data around. But then the central processing unit, or CPU, needs to know where to find data. So it needs what's called an address bus. And that's a way to put data and get data into a specific place, rather than just particularly moving around. And then there is the control bus. And the control bus is how all the operations are controlled. If we look at the Java virtual machine analogy, we can think of the stack, the LIFO stack, as being the CPU. We can think of the heap and the constant pool. We'll talk a bit more about this more later, what these words mean. But we can think of what the Java virtual machine calls its heap and constant pool as being the place for memory, or the registers if you like. Now, what is this thing called the cache? In early computers, as the amount of data and the complexity of the programs increased, computer scientists found their computers going slower all the time. So they looked at ways, how can we speed the computer up? And one of the first ways employed to speed computers up was to create what's called a cache. And this is a special area of fast memory that lives close to the CPU. And data that was used a lot, important data, could be stored in the cache where it was quicker. It was a lot quicker to get the data from the cache than from the normal memory. And in the Java virtual machine, we have an analogy with this thing called the just-in-time compiler, or the JIT. And it acts a bit like a cache. Its primary job is to speed up the Java virtual machine. And it does this by getting the data from the main data store, if you like, and processing it in a special way, just as the cache would have a replica of the data in the main memory, but because it's in special fast memory, it could be processed in a special way. So it's good to see the analogies between the parts of a simple computer and the Java virtual machine, or the virtual computer. So the cache is a special part of a simple computer to speed things up when the computer is running, and the analogy in the Java virtual machine is the just-in-time compiler, which speeds things up at runtime. Then we have the main memory area, the registers in the simple computer. Then we have in the Java virtual machine the heap and the constant pool. Then we have the central processing unit, or the CPU, and in the Java virtual machine we have what we call the LIFO stack. Now, the control bus controls the way decisions are made. We can think of that as being the heuristics of a just-in-time compiler. Now, heuristics are a set of rules that the just-in-time compiler uses to make decisions about how it's going to process the data to speed it up. Also, in the Java virtual machine, we have a whole extra area of software that it needs at runtime, like system resources, class loaders, and the standard language packages of Java. Now we've looked at the analogy between a real computer and the Java virtual computer. And this Java virtual machine can establish a process. A process is like an isolated part of the operating system that can run and do things. So a Java virtual machine is a process in itself, but it can create child processes, and these are called threads. And each thread has its own reserved memory area. So in the main memory there will be a portion reserved for each thread the parent Java virtual machine process creates. And it has its own memory area, but it has more than this, and so we'll go through the main points. Each child process or thread created by the Java virtual machine has its own stack, and these stacks can store a special construct called a frame. A frame is created each time a method is invoked and consists of its own stack, an array of variables, and a reference to what's called the constant pool. This is the part of the memory where the Java virtual machine stores constants, things that do not change. We need to think of the Java virtual machine as a virtual device used to interpret Java bytecodes. It executes the bytecodes, handles exceptions, and manages almost all the RAM in the computer that it has access to, and handle the simultaneous execution of multiple threads. So the Java virtual machine is a powerful virtual computer. It's helpful to think of this in terms of layers of function, and we'll go through them. And the higher layer down to the lower layer we abstract. So our programs run in this top layer, and this is abstracted or hidden away from the layer underneath, and that abstraction goes down, and that abstraction helps us deal with the complexity. Let's look at our understanding of a Java virtual machine with reference to this layers approach, where we look at the different parts as layers, and remember, each layer is hidden away from the layer below, so the process and threads layer doesn't know that much about what's happening at the layer below, the JVM layer. So let's start. This is where we think of when we write code. When we write our Java code, we're writing it to run at this level, and we're thinking at this level. We're thinking about our main process that can create child processes called threads. That main process is our Java application, or sometimes we can think of the application and the JVM as being the same thing. Now, the Java virtual machine virtual processor. When we compile our Java program, it creates what are called bytecodes. Now these are bytes, and the Java Virtual Machine's virtual processor reads those bytes and translates them into instructions at runtime. So just as a real processor reads machine codes to run the operating system, the virtual processor reads the bytecodes to run the Java Virtual Machine or process. When we compile, we create bytecodes, so we have a bytecode layer. So the bytecodes exist there in the file system, and the virtual processor of the Java Virtual Machine reads them. Then below this layer we have the native code. The native code is the real code that the real processor runs. The operating system is the kernel. It is the system that provides the instructions to the real hardware to interpret the native code of a program. And below this layer we have the real processor and memory. So the real processor and memory support an operating system. In that operating system we can have binary programs or executables. One such is the Java runtime environment, or it could be a graphics package or an audio package. And these binary runtimes or executables read native code to perform their instructions. So the bytecode that we create when we compile a Java program exists a layer above the native code. The Java machine's virtual processor reads the bytecode to execute instructions, so it's a layer above the bytecode. And when the Java Virtual Machine's virtual processor executes instructions, this is what runs our Java Virtual Machine process and its subprocessors called threads. In operating systems, the process is the abstraction that separates the kernel from applications, and applications from each other, while sharing systems resources. So that's a general definition of a process, and our Java Virtual Machine is a process. So these are the layers. This helps to clarify a little bit about what's going on. And this concludes our discussion of the Java Virtual Machine architecture. It's important to understand to the best of your ability the tools you work with. And while we are not computer engineers or hardware engineers, the more better understanding we have of the hardware, real or virtual, that we program when we write our code, the better results we will obtain. I encourage you to refer to this document again as we progress through the syllabus to try and relate what you learn to the underlying machine that you're working with.